Hello everybody, welcome to our Chapter 9 class on Plasma Physics 1. This is a chapter on microscopic equations for conducting fluid, and I'm going to start talking about the end of Chapter 8. You had on Chapter 8 there was this discussion about cold plasmas, warm plasmas, and hot plasmas. Well, this is the way we're gonna approach these definitions is based on the sets of equations that we're going to use to describe those plasmas. So in this course we have some chapters dealing with particle motion, individual particle motions, and then when you have a non-collisional plasma, usually you want a kinetic description of a plasma. You want to know where every particle is going. But sometimes if you have collisional plasmas, the frequency of collisions is high enough, then you would like to treat your plasma as a fluid. And in Chapter 8, there was this derivation of macroscopic equations of a plasma, where an equation is obtained for each species, each alpha species. So you have an equation for ions and an equation for electrons, and you may have different types of ions. So you have an equation for each species. And then if you consider only the continuity equation and the momentum equation, then you're thinking about the cold plasma. So you're assuming that your pressure diet is null. It's zero. There's no pressure, so the temperature is actually zero in your plasma. So it's a simplification, and this model is good to study electromagnetic waves in slow amplitude with phase velocities much larger than thermal velocities. So in this equation, in this case of cold plasmas, you're dealing only with continuity and momentum equations. Okay, so you have the pressure is zero. Then in a warm plasma, you add the energy equation. Things start to get more interesting here. So you actually have some temperature. And but you would suppose that there is a simplification in your equation. You drop the term responsible for the heat flow without heat flow. So in this case, there is no energy flow. It's still valid if you have phase velocities much larger than thermal velocities in your systems, but it's a much better approximation than the cold plasma approximation. This is called adiabatic approximation. And you have a zero thermal conductivity. There's no viscosity in your plasma, and if you think about the pressure diet tensor, there are no terms in the outside the main diagonal, so there's zero outside the diagonal, and the terms in the diagonal are all equal. You have only a single pressure, so you actually have a scalar pressure. Scalar pressure for each particle, alpha particle. If additionally you suppose that the energy change by collisions is negligible, then the energy equation may be further simplified and you get the adiabatic equation. So how can I summarize this? Let's just say energy change if energy change due to collisions is negligible, then you get this equation for pressure. This is the mass density of alpha particle to the power of minus gamma, and this is constant. So this is your state equation. In this case, gamma is just n plus 2 over n is dimensional space dimension. That means you may be in 2D or 3D, so that's n. This is the adiabatic equation. So our hot plasma is different. In this case, you're completely out of equilibrium. So you do need heat flow in this case, and viscosity and everything. You need the whole microscopic equations to describe this plasma. Okay, so this is just a basic review of the end of the previous chapter, so that we can catch up from here. In this chapter 9, we're basically sum the equations derived in previous chapters over all alpha particles. So we have one continuity equation for each alpha particle. We're going to sum all of them and obtain a single equation for a volume element in your flow. So we're no longer considering differences between particles in this particle types in this chapter. So, like if, for instance, you had the mass density, which was given like this. You had an equation for the mass density of each species, and now we're going to sum over all species. So this is our first equation for this chapter, and we're going to do basically this class. We're going to just do summing. But it's not always that simple. Sometimes we get some very complicated equations and we would like to simplify them. So in the summing process, we will try to make some simplifications. So this is the mass density, and for the charge density, you have something similar. This is charge density. You just, in place of mass, you have the charge and the number of particles. You do have mean flow velocity, which will be denoted by U. And this is given by this equation. You sum the mass density times the mean velocity of the alpha particle. So I'm going to sum everything in the alpha particles multiplied by mass density and divided by this mass density of the volume. So U is actually the mean of U alpha with weights. It's the weighted average of the U alpha. The weighting is important in this definition because particles that have more mass will contribute more with the velocity of the plasma. So this is why it's important to multiply it by the mass density. If you want the mean velocity of each species in a frame moving with the mean velocity U, then you get the diffusion velocity. Diffusion velocity is denoted by W, This is for each species. You get this expression. So you have the difference between the mean velocity of each particles and the mean velocity of your plasma. And in our case, we can use then this definition here. So we're just doing some summings at the moment. Now we can define also the flow, or the mass flow, or mass current density. I prefer the term mass current density for this. Sometimes they call it mass flow, but it's given like this. We have a sum over alpha particles of the number of particles times the mass of each particle times the average velocity of that particle. So if you use this definition for the rho, you have just this, right? And for the sum of u is like this. I forgot the number of this. This is 1.3. Okay, so this is the charge flow, sorry, the mass flow, and then we have the charge flow or electric current density. The current density will be given by J, capital J, which is the sum over alpha of an alpha Q in place of M and this here. If you use, let's see, 1.4 here, I'll use in place of this omega plus U. Oh, sorry. And alpha Q alpha U plus omega alpha. So if you consider this part of the sum here, NQU, then using 1.2, NQ is rho, so it's rho times U, right? So this is rho U, I think I'll write it down here. So J is actually rho times U plus then the other part. And alpha Q alpha omega alpha. Well, from chapter 6, we have the pressure diet. From chapter 6. The pressure diet was defined by rho m alpha, C alpha, C alpha, where you had, this is 1.7, where you had C alpha equal to V minus U alpha, right? So it's basically the difference between the particle velocity and the mean velocity of the alpha particles. This definition then is valid for particles going through a surface of a fluid element moving with the mean velocity of the particles. So we are considering this type of fluctuation velocity in the computation of the particle. But for a plasma as a whole, it's useful to define also this other quantity, C alpha naught, which will be the difference between V, the particle velocity, and the mean velocity computed over all particles. So this is going to be 1.8. We'll use in into the sum of 1.7. So for the, we're going to compute it basically on the total pressure. So we define the total pressure to be sum of alpha particles, this, but here instead of C alpha, we use C alpha 0. By using U equal to U alpha minus omega alpha, and this is just the definition of U. This is from 1.4, right? Yeah, it's here. 1.4, and V equal to C alpha plus U alpha. In 1.8 we get, well, then C alpha 0 is C alpha plus, and here U alpha minus U alpha plus omega alpha. Okay, so we get another definition for another way of writing this equation. This is 1.10. So I'm just deriving some basic variables that we are going to use when we write the MHD equations, the magnetohydrodynamic equations. So these initial steps are very important. So now I'm going to use 1.10 into 1.9 here. So 1.10 into 1.9, we get, oh, this is for the pressure, right? Total pressure is the sum of rho M alpha C alpha plus omega alpha in place of this. Then there's a tensor product with C alpha plus omega alpha here. Now, what we can do now is apply the distribution here in this product operation, and we get P equal to, it's the sum of rho M alpha times, well, we have first CC, then CW, then WC, which is the same as CW, and, well, actually this is tensor. So, well, anyway, let's write both things, not commutable. C alpha plus, I better keep the order of the variables here because this is not a scalar product, it's a tensor product. So let's keep both separated here. Plus the final one is like this, 1.12. But the average value of omega is, by definition of omega, this is U minus U alpha minus U, which is U alpha, the average of U alpha minus average mean value of U. But this is an average in alpha. The average in alpha of U alpha is U alpha. We have shown this in chapter 6. It's equation, I think, 1.12, maybe. Well, this was shown formally in chapter 6. You may want to check it again. So, and this is not a function of alpha, so the average in alpha is u itself. And this is the very definition of omega alpha. So here's what was expected. The average of alpha in omega, of omega alpha in alpha is omega alpha. It's the same as with u. So the same happened here. This average is the u itself. This average is also u itself. I think I'm going to call this one 1.12, 1.12 prime. Maybe I'll use this equation later. Okay, so what we have is that this product, and there's an arrow here, this product, which may be written like this, because you have this average, which is, I'm using this result here for omega, and this is 0. Why is it 0? Because this is fluctuation velocity. Remember that the mean of the fluctuation is 0. We show this in chapter 6 as well. For the mean of this is 0. See chapter 6. I think it's equation 622. Chapter 6, equation 2.2, I think. Let me check it. So we may rewrite equation 1.12 as P. In this case, the pressure will be alpha of rho C. So we end up with less terms. This plus then this times this, right? But we don't need the brackets here because I have shown that you don't need the brackets in this average. So we just write it like this. And using a tensor notation, I can write P alpha for this. And why P alpha? Because check the equation, it's like this, right? So same thing here, plus this sum. Now, there's another definition which is important for us, which is the total scalar pressure. The total scalar pressure was 1/3, and will be here as well, times the trace of the total pressure. Actually, I had defined this for alpha particles. Now I'm just dropping the alpha and keeping the same definition for the total pressure. Then we have the total scalar pressure. So the trace is, remember, just the sum of the main elements of the main diagonal. So I get 1/3 times the sum of pressure is a tensor with 3 elements in the main diagonal. So I'm just summing the elements of the main diagonal of this matrix. And this is using the definition of each element 1/3. I am summing in particle alpha because, well, because of where is it? Because of this, right? The P has a sum overall of particles. So if I want to show the elements of this tensor, I have this. Sorry, not this tensor, the element of this tensor. So I have this times C alpha 0I, C alpha 0I. This is the multiplication element by element, and you end up with this expression. C alpha not square. Another way of writing it, a shorter way. We have another vector here, which is the total heat flow vector. The total heat flow vector will be this. You may compare it with the expression 7.2 of chapter 6. So what we are doing is just summing the elements of that heat flow vector for alpha particles. And also we define the thermal energy density. Thermal energy density is 1/2 times the sum of mass density times fluctuation velocity square. Thermal energy is like kinetic energy, where you have 1/2 mass times velocity square. But for the thermal energy, in place of V, we're using fluctuation velocity or random velocity. That's how we define it. And if you compare it with 1.14, you see this is P, right? So P is equal to this. So comparing both equations, we can see that this is actually 3P over 2, an important quantity for us also. This is going to be our dependent variable in the energy equation, be derived later. Okay, and for isotropic plasmas, isotropic plasmas, where what's an isotropic plasma? You have the alpha pressure equal to a scalar pressure times tensor identity matrix, right? So it's just the same element in each element, the same P in each element of the main diagonal. So in this case, it can be shown that the heat flow vector, total heat flow vector, is equal to this 5/2 P alpha omega, this is a scalar, plus 1/2 mass density, this square, and this. Which is an expression that you'll have to check equation 1.22 in the book. I'll not derive this equation, so you go check the equation, how he derived this one in the book. So if you compare it with, where is our previous, okay, here. You have this equation, it's a tensor equation. If you have scalar pressure, then you end up with this alternative equation. It seems more complex than the previous one, but you don't have this, it's actually more complex. So why bothering? But it's another way of writing it, may be useful when you have information about omega alpha. Okay, now let's start with the real thing, continuity equation. We will derive the magnetohydrodynamic equations starting with this one. From chapter 8, equation 3.2, from 8.3.2, you have this equation, which is the continuity equation for each species. And you have a collisional term at the right. So this collision. Well, we are now summing overall alpha species, right? So what we're going to do is just draw a summation symbol here. But then, if you sum over alpha, you get alpha del m alpha del t plus this equal to alpha s alpha. Okay, but this is actually 0. Why? Because of conservation of total mass in your system. So you don't want mass being added to your system due to collisions. So we set this up to 2.1 is 0 when you sum overall collisional the collision term for all species. Okay, then we have actually this. Okay, equal to 0. We just drop the summation because we have already defined these quantities. And this, we can employ the rule of product here for this divergence and rewrite it like this. Or you can merge these two terms into one single term using this material derivative symbol. It's basically the same thing. 2.3. So dt is just this differential operator. Okay, this is our continuity equation, the first equation for our magnetohydrodynamics equations. Now let's do the equation of motion. Oops. Okay, we start by summing equation 8.4.9. So from chapter 8, equation 4.9, I'm just going to sum the elements of that equation. So we get the summation here. Electric field plus we have information about Lorentz force, then we had gravity. This is just Newton's second law of motion, right? Minus, then we have pressure. We're just adding all the forces. Plus the sum over A alpha minus the term involving collisions. Okay. Well, A alpha is the rate of change of momentum, or mean momentum by unit volume due to collisions. So these are both contributions of collisions. Well, since the total momentum of particles in a plasma is conserved, we also have this equal to 0. Now we're going to use using 1.1 for the mass density, 1.2 for charge density, 1.6 for current density, and 1.13 for the pressure. We get this equation. Still summing here. Okay, I'll keep this sum in the left-hand side. You still alpha particles in here. Oh, sorry, this is not rounded, this is squared, right? And in the right-hand side, now we use these equations to write rho E, then J cross B, then rho mg minus divergence of P plus the sum of, what is this? I don't have P. Okay, actually in 1.13 what we had is like this. The sum of P alpha is P minus, so let's check this. 1.13, I forgot about this. What is 1.13? 1.13 here. Okay, P is alpha, P alpha plus this contribution of omega alpha. So this is what I was forgetting to add here. So we have this plus, when I sum this, I get this plus this other term here. Omega alpha minus this. Okay, we can treat this last term in 3.2 using the definition of S alpha. What is S alpha? S alpha is, it's here, the 2.1. The sum of it is the sum of this. So S alpha is just del rho del t plus the divergence of this quantity. So I'll multiply this by U. So we know that U alpha S alpha is actually U alpha plus rho M alpha T plus this divergence. Be careful here, you cannot say this is 0 just because I said the sum of it is 0. The sum of it is 0, but now I'm summing it multiplied by U. So we don't know if it's 0. So I have to add this, which is 3.3. Now, if I use this result with the left-hand side of equation 3.2, let me see here, 3.2. So we have this. And I'll just move this term to the left using 3.3. So using 3.3 in the equation 3.2. 3.2. We have, what is the beginning? It's alpha omega. Okay, alpha omega, that's correct. Del U alpha del T plus U alpha dot nabla U alpha plus U alpha rho, well, just that. And this is equal to all the other terms. Now we can rewrite this two terms like this. Rho m alpha u plus alpha u alpha u alpha, right? This is the you have these two terms, right? You have this times derivative of this plus derivative of this times this, which is here, and the same for the product rule for using divergence, combining these two terms. So this is the same thing, and perhaps I should write the other terms here, which are this, right? J cross B rho gravity minus divergence of pressure plus the alpha sum of divergence of, okay, divergence of rho alpha omega omega. All right, this is 3.4. Now we have to think about this term here. We can rewrite it as well. Let's treat this term. The left hand side is, what do I have? Rho u plus divergence rho u alpha, right? This is ugly. Okay, if I sum this first term, I get just the rho, the mass density, total mass density, times u. So we have already done this. I know it's this, right? I don't need the summation here. Plus, well, I'm just going to represent u by the sum of omega and u. So we have here rho times, what is u? U is, let's see, 1.4. Or is it? It's too many pages. 1.4. Oh, here. So u alpha is omega plus u. U alpha is omega alpha plus u. omega alpha plus u. (1.4). Okay, so what we get is, I have this, just keep it here, plus, now I'll distribute this product here, and I have the divergence of rho omega omega plus rho omega u plus rho alpha u omega alpha plus rho u u. Okay, which we can use now again the definition of omega to get this is plus the sum on alpha of the divergence of this first term, and I'll split the sums. So I have, well, the divergence is a linear operation. I can remove it from the sum. I can write it like this: sum of rho u in place of, I'm here, in place of omega in this term, I'm going to use u alpha minus u times u. Okay, this was this. For this one, we have something similar. I get divergence of the sum and alpha of rho omega alpha u alpha minus u plus alpha, again the divergence here, right? Let's remove it from the sum. Divergence of alpha rho m alpha u u. Okay, now what do we get here? Don't need this. If you sum over here, you have just rho m times u minus rho m times u, times u, so this is 0. This is going to be 0. And the same here, it's going to be rho m u minus rho m u. So this is also, after you sum, you get 0. And you end up with only this one. So after all that, we end up with this omega plus the divergence of, I have summed in alpha here, I have just this. Now, I can apply the product rule for this divergence. It's divergence of all this, right? So this can be rewritten like this. I'm being very cumbersome in this derivation because in the book you don't have all the steps, and I think it's useful for you to see all the steps. If you don't want it, you just skip this part of the video, but it's important for you to know where things came from. So apply the product here. It may be written like this. Okay, almost there. Now what I'm going to do is the product here. The derivative of the product is u times the derivative of the second term plus the second term times the derivative of the first term. And for the rest here, I can just write it like this, just repeat here. Rho m u plus u divergence of rho m u. Now what do we need? Oh, good. This is good. Look at this. You have, I'll just put this in evidence here, multiplying the derivative of u and t plus u dot now u for the first two terms. Then I have alpha, this times this, just repeating this term, plus what? Plus u here times, let me see. Okay, you'll get this one here. I joined these two here. Now I'll get this one and add with the other. So this is rho, sorry, this is here, this is here. Now this comes here. This comes here, and the other term, the last term is this. Voila! What is this? What is this final term? We know it. It's somewhere around here. Where is it? Okay, here it is. Continuity equation. It's equal to 0. Good. One term less. So this is continuity equation. It is equal to 0 because of 2.2. Okay, this is it. We can keep the other terms and write the equation like this. Rho m. I'll just use the notation of that capital D for this term. So this notation here, right? For the two first terms, and this. Divergence of this. .6. Now we can use 3.6 into 3 point, where is it? 3 point, I think it's 3.2. Yeah, 3.2. Using 3.6 and 3.2, we get rho du dt plus alpha divergence of this equals rho e plus j cross b plus rho mg plus, no, minus the gradient of p plus, what was the final term? 3.2. 3.2 is, well, this one, right? Because I had switched this to the left side. Actually, I'm doing, it's not 3.2, it's 3.4 is the best one, right? I'm working with this one, it's 3.4. 3.4, right? Yep, and the final term is this, yeah. So 3.4, not 3.2. the 3.4. Then we have it here, plus the sum and alpha of divergence alpha omega omega. And not by coincidence, this is equal to this, and we can remove it, and this is our final equation of motion. Okay, this is rho E, electric field, current, magnetic field, gravity, and pressure gradient. That's the equation of motion. Next, we're going to derive the energy equation.